Okay, thank you everybody for staying up and awake so late in the day after so many days. Welcome to my talk on crypto failures, where I hope to take the next 30 minutes and walk you through some interesting failures in crypto usages more than implementations, which I find to be most of the issues when people use cryptography libraries. So my name is GUY BANHART MAGEN. I'm a security consultant today, also some track record in startup companies, some large enterprises. I also speak quite a bit, usually on the offensive side. I run B-Sides Tel Aviv, which is a very large conference in June during Cyber Week, about 1,200 people. And it's more geared into the security research community, which I am part of and often speak at. Before I begin, I want to take 30 seconds of your time and to rant on something personal to me. I think that it's wrong that OWASP decided to invite a keynote from a company called NSO, which you might be familiar with, the malware named Pegasus, and various incidents around the world, from going after gay people in Turkey, from murdering Mexican students in Mexico City, to a lot of other places around the world. But most importantly, I think that a security company that is built on monetizing and weaponizing security vulnerabilities should not have a front stage seat in a security community conference. And with that, I'll continue. Thank you. I'm not going to go into math, so if you're afraid of math, you're in the right place. We don't have time to really go into that, but I do want to remind you a couple of important things. The first three acronyms is CIA, which is a good acronym which we all like and hope. Confidentiality, integrity, and authenticity. This is just for background, so we are speaking the same language. Hash functions. A lot of people know what hash functions are. Not all of them understand what exactly do they mean. And the reason I say that is because I have conversation with developers, and they often use the phrase, I'm encrypting this with SHA-1, which is wrong, but not just from a mathematical perspective, but just from a conceptual and usage perspective. So in order to understand what a hash is, it's a one-way function, meaning that I will take some input and get some garbage at the end, and that specific garbage has unique properties. And if it's not held to these unique properties, this is not a cryptographic hash. So whenever you read somewhere or look for something and you hear someone say hash, you should ask yourself, what exactly do they mean? And the litmus test here is that if you change a single bit in the input, you should have a very wide distribution of change over the output. So you can see the letter D change to the letter C here, and that really changes the output, which you can see bolded. Okay. Generally speaking, hash functions, cryptographic hash functions, were thought to be relatively impervious to attacks. So SHA-1 used to be too big, too cumbersome to brute force, but with the current state of the art, we are talking about the reduction from 2 to the power of 80 to 2 to the power of 68, which realistically speaking is about $100,000 of EC2 instances. So this is not something that I can spin up at home, but this is not exactly far away from a company who wants to do this for commercial use, or definitely not for any kind of government. Symmetric encryption in general, we are very familiar with AES. There are a couple of other options as well. And here we are also expecting the same kind of properties. If we take some sort of message and we want to encrypt it with a key, we will need a property that says if I change a single bit in the input, I will get a very nicely randomly distributed output. This is my expectation. If this is not happening, that means that this is not a really good cryptography scheme. Another thing is that we do have an expectation on the size of the input, the size of the output, and stuff like that. The reason I'm mentioning it is because those sizes leak information about what kind of scheme you're using and what types of things you can expect. For example, if you remember the LinkedIn breach that was about 3-4 years ago, I think it was somewhere on the order of 50 million records that were leaked out. And in that database, all of the passwords were encrypted, but it was almost rudimentally easy to understand what kind of scheme and the fact that they use the same password, because you could see that there are repeated blocks. And all blocks were a factor of 56 bits. so the block size was 56 bits. And you can actually look at the data and just analyze it and get into those kinds of results. So you know it was blowfish, and then you can take other steps on top of that. And they use the same key for all of the different 50 million records, because you could see different records that are encrypted into the same value. So people who had the same password got the same encrypted, stored text in the database. Public-private cryptography is a bit more difficult to explain. And people who are using it usually use it in a very high-level manner or in a way that's not exactly as the author intended. And this is important. So basically, we have a way to generate a public and private key. They have some properties. I'm not going to go into them. And you want to give everybody your public key, so they can just create new messages and encrypt them with a public key. But because you hold the private key, you can decrypt it. So that's the basic of a public-private key scheme. There are some assumptions here. The assumptions here is that the operation of encrypting something or the operation of decrypting something is not the same. They are held into different kind of schemes. For example, if I am the server and I want to prove to the world that I'm the owner of a specific public key, then I need to hold the private key in order to perform computations with it. So when you're spinning up a server and you want to put a certificate on it, a certificate is fine for some use cases, but if you want to actually do a full-way communication, you have to prove that you're the owner, and you actually have to hold the private key, which might be an issue. There are other ways to deploy it without holding that private key. Signatures is the way that usually stuff like that sort of boils down together. When you're talking about signatures, you want to actually to prove to someone that you hold an identity. An identity might be anything from me claiming to be Guy Barnhart Magen, and I can prove that I am Guy by showing you a proof that I have the private key. But more than that, I want to show to the world that I am that owner of the key, and the scheme to do that would be something like this. I will take a message with a hash function, I will save the hash of that message. And then I want to encrypt the hash of that message with a private key and get a signature. Now, everybody in the world can take my public key, which I said it was mine, but I don't have any way to prove it, but then they can compute the hash of the message themselves and get some H tag, compare it to the decrypted message, which they can decrypt because they have the public key, which I claim to be mine, but I haven't proved yet. And if H is the same as H tag, that means that whoever created that encrypted message was holding the private key. Therefore, I am who I say I am. So this is a signature scheme, very high level, hand wavy kind of thing. Random. Another very important component of cryptography, and basically what it means that I want a random source. It means that whenever I pull a bit from the source, I don't have any way to determine what the next bit is going to be with a better chance than 50%. That means I am asking from a source to give me more bits. It might be 0, it might be 1, but I don't have any way to predict if it's going to be 0 or 1. If it is, this is not a very good random source. So the two basic components we usually talk about are a TRNG and a PRNG, maybe some places call it DRBG. But basic thing is, if it's a true random number generator, a couple of oscillators, maybe something that's related to a breakdown of isotopes, stuff like that, which is hardware in the real world, will actually put out bits with some probability. However, what we all use everywhere is called PRNG. PRNG is pseudo-random number generator, which is basically saying, I have a predictable way to cause unpredictable outputs. Or, in other words, I will put in some sort of seed, some sort of input, and I will hash the result, and I will hash the result again, and hash it again, 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 and again. And if I'm using a cryptographic hash, then I can show that I cannot predict what the output is going to be. Therefore, the output looks to be random. It's not really random, because if I am aware of what the seed is, I can predict the entire chain up to the moment where you are actually putting the bits out of the system. So what happens when the random isn't random? And that is a good question to ask. But also, whenever you are implementing or using some sort of implementation, and somewhere along the line is written something like nonce, or it's a temporary value or a temporarily random value, and people treat it as non-cryptographically secure element, or I just copy it from the other implementation that I had, or stuff like that, bad things happen. And this is the first thing that what I want to talk about. So, how many of you have heard of Bitcoins? At least one, yeah, maybe. So, basically speaking, Bitcoin or the Bitcoin protocol is sitting on top of something called blockchain, which is basically cryptography in the real world. So, a couple of examples which will help us understand. A coin basically is, I want to find two different inputs that will provide, or I want to find an input that will provide a hash result. So it's not a very easy thing to do, but it's possible if you dedicate enough CPU cycles. And the result of that computation is basically a coin. So we're talking about Bitcoin. It's actually me investing a lot of mining operation, a lot of CPU cycles to find an input that will have a specific hash output. Wallets are basically the private keys, public keys that you have. The hashed results of those addresses are the wallets or the addresses for the Bitcoin protocol. And transactions, moving money from wallet A to wallet B, is basically me signing with my private key an order that says move funds from wallet A to the destination wallet B of this amount, and I affirm this action with my private key. So this is a blockchain transaction, basically. Okay. An important thing to note here is that because the identity is strictly tied to your private key, if you lose your private key, you lost your money. There is no way to move money out of that wallet if you lost your private key, because you cannot create it, you don't have any tool, any way to create a transaction that will move money out of that wallet without providing the private key. And it's very interesting because the vice versa also happens. If somebody else has your private key, he can move funds outside of your wallet without anybody being able to prove that it wasn't you moving the funds out of that wallet. So it's a difficult thing to grasp when you are designing the system, that things can break both ways. And here I want to show you an example, a specific implementation of public key cryptography called elliptic curves. Anybody heard of ECC? 6 people? Okay. So 7 with Itzik. So I'm going to wave my hands a bit. Elliptic curves, I'm not going to explain what it is. It's just a different scheme to provide private and public keys. But in this scheme, which is used by Bitcoin, is very tightly coupled to the randoms that you're using. So part of the scheme is the choice of the random numbers. And if you're not choosing them correctly, you're going to have a bad time. And I'll show examples. A transaction is basically, this is the money I can spend and I move it into this account. Or something that looks like this. So on the left you have the addresses, which is the hash of the key. And on the right you have the breakdown of where do you want to transfer your Bitcoin values. So it's a float, so you can see a lot of accuracy after the decimal period. But the bottom line is, once I submit this transaction, it gets registered on the blockchain, and then officially this money has moved from wallet A to wallet B. Okay. So in order to understand the operations, and this is the bit of a mathy thing, but I will wave my hand here, you have a couple of different things that come into play. So there's some known parameters for the curve, for the algorithm, which we would just call them G. And we have H, which is the hash of the message. We have our D, this is our private key. And we have K, which is a random number. I point your attention to K. And basically what it means that when I sign something, I do this operation here on the bottom right, which is I add something, I multiply something, I divide something, and this is basically the signature. But this is problematic. It's problematic because people who write wallet software made assumptions. And they made assumptions, for example, that this number K needs to be random. They read the spec. They didn't understand that it needs to be random each and every time you perform a transaction. So why is that important? Well, assume that you have two different transactions performed by the same wallet software, and both transactions had the same key because they did not choose a different random for each transaction. That means that you can now take two different values of R, comma S and do some additions, subtractions, multiplications, some algebraic work, and you can extract K. And once you know K, you can extract S. And once you know S, you can extract D, the private key. Once you have the private key, you have the money. So this is from when the actual attack started in 2013, August 10, 2013. And somebody posted messages on the boards. We're getting a lot of feedback that people are seeing transactions that they didn't actually do. Does anybody know what's going on? Well, the answer was somebody understood what's going on and just funneled all of the money into different wallets. And you would assume, okay, this is like a bad bug. This shouldn't really happen, but it happens that there are bugs. But then you see that this kind of things keeps happening every quarter, every 6 months. Some wallet software is getting hacked. And when you look into the hack, you understand that they actually implemented the software wrong. They didn't understand how to implement ECC correctly. So I hope this is an example which was illustrative enough of how this actually works in Bitcoin. But that's not the only place that these kind of things happen. For example, you would expect when somebody is trying to get a random value, they would go to the system, to the kernel or something similar, and they will read, for example, from /dev random or /dev urandom, get some bytes and store them. And that's true, that's what should happen. What should not happen is you take those bytes and store them as static keys or static values. So what happened with Sony PlayStation 3 a couple of years ago is that a very nice group called Failoverflow looked into the signature scheme for the downloadable content and patches for the Sony PlayStation 3. And what they found when they compared different downloads, different patches, they were all signed with the same key, and all those keys were using the same random value. So they just did some algebraic operations and found the private key, and lo and behold, now everybody has hacked PlayStation 3. So it's not like there's something that you can easily recover from when you're leaking your private keys out to the world. This is a major issue. And it's not because somebody didn't think about security, he just didn't understand the cryptography behind it. Another thing that's important to note and is the difference between anonymity and confidentiality. And the basic tenet is that I can be anonymous. It does not mean that I can hide what I'm doing. So on the blockchain, on Bitcoin, everybody knows what you're doing. Every time that you're moving funds from wallet A to wallet B, from B to C, from C to D, it's all logged, it's all registered, it's all shared. That's the basic way that the distributed chain is working. On the other hand, it does not necessarily have any kind of identity tied into it. But if you want to move money from Bitcoin out to the real world, or from the real world back into the Bitcoin, some identity has to be involved. Somebody has to give their credit card details. Somebody has to go and give real money to get fake Bitcoins. So this is something that some malware people forgot or didn't really think through. And this is a very nice example. You all remember this screen 2.5 years ago, more or less, 2 years ago, around May? So I kept tabs on this, and it was very interesting because for about 7 to 9 months, they had money funneling into their wallet. The WannaCry people had money funneled into the wallet, about $100,000 more or less. They didn't touch it. They couldn't touch it because there was so much attention on that wallet that if somebody went and converted it into real currencies anywhere in the world, the Interpol would be all over them. So anonymity and confidentiality are not the same thing. By the way, they solved this problem in the end by using something called Bitcoin mixers, where they split the money into a lot of different components and send it into different wallets, then recombine them in the end for the other agencies, etc. It's not unsolvable, you just have to think it through. So this is a case of how bad crypto looks by design. I want to show you a couple of other examples. Do you remember this piece of code? At least one person? Okay. 2%, wow. This is very interesting. This is a piece of code that was used, if I remember correctly, by Apple in their certificate verification code. And what this code actually means is that I'm trying to verify that a specific certificate belongs to a service. So I will check A, and I will check B, and I will check C, and in the end I will come to the conclusion that this is a valid certificate. And if one of the checks would fail, then I should maybe not trust that certificate and do something about it. But somebody did this, probably by mistake. And what this code now means is that I will check this, and I will check this, and I will check this, and if I haven't found any fault up till now, I will go to fail, and because fail is being called without a failed state, it will exit with a non-error status code. Which means I can craft a certificate that would be completely malicious. As long as I fulfill the first kind of issues, it will not trigger any kind of alarm, and it will fail out of the code with a correct status code, with a verified and secure status code. So this was a very interesting vulnerability in the sense that it's not that somebody did it maliciously, most probably. There are rumors about NSA doing stuff that's probably not true. And somebody just copy and pasted code. Pasted the line and double pasted it, and it's pretty not that easy to find out in code reviews, etc., that there's a double go-to here. But it has huge ramifications. So when you audit the code, you understand that somebody can just bypass your entire mechanism. Okay. Another interesting aspect is BitLocker. How many of you use BitLocker on your laptops? Do you enjoy it? Did you do it on purpose? No, I'm joking. So a very interesting work was work on a couple of different SSD vendors that supported the BitLocker, or actually supported an encryption scheme, and BitLocker was using that encryption scheme. And the way that it works is BitLocker will use the encryption on the hardware if it's available, because encryption closer to the hardware by hardware components is much faster than using CPU cycles to perform the same kind of work. But there is an underlying assumption here. There is an underlying assumption here, and that is that the code that's running on the piece of hardware on your SSD is secure. So, and a very nice group of people looked into it and found that it wasn't as secure as that you would assume. So the password and the data encryption key were not linked, basically meaning that there's no connection between the password that you're using to type into your BitLocker interface and the key that is used to encrypt your drive. So if somebody can break your, can just pull the image and look at your token, at your key, he can decrypt the entire drive because it has no ramification on actually knowing the user password. So the entire evil maid attack, or whatever you want to call it, has no dependency on me understanding what your BitLocker password is. It just doesn't matter. Another thing is the entire disk was being encrypted with the same key. So that means that if I understood how to decrypt one file or one block, I can understand how to decrypt the entire disk, all of the blocks. And the most important thing is that the DEK was not random. It was predictably chosen and could be predictably scripted in order to understand, well, you have a very nice SSD, you use BitLocker on it, but I don't need your password, I just need to understand the key, and the key is not random, it is deterministic, I can find out what it is. It's tied to the hardware identifiers such as your serial number and your model type, stuff like that. Which means that if I have access to the device, I can probably discern the key and decrypt the entire drive. Another thing which was very interesting was a feature called wear leveling. This is more hardware oriented. How do you prevent your SSD from wearing out? What it means is if you write something into the disk and then you erase it and want to write it into somewhere else, it will not overwrite the same space. It will try to write into other spaces first. Which means that there are pieces in memory which were once holding secure content and they are erased, meaning there's no pointer pointing to them anymore. But now I can go and read those values and they're still containing the passwords, the keys that I want. So this feature, which was very beneficial from a disk wear out kind of thing, is very beneficial for security because now I can just go and read if the old password or stuff like that. And of course, the time-honored favorite, just use zeros for password, because that's always a good idea. So what happened with the BitLocker is that it was shown because BitLocker preferred to work with whatever the hardware device was offering. It was often less secure than it was actually doing the same thing in software. And the software implementation of BitLocker was actually pretty good, but it was not used because there was a flag, use hardware first. Okay, another example, and this is just a funny one. There's a very nice utility, which I currently forgot its name. Well, I'll talk about it in a moment. But somebody had a discussion on Twitter, on LinkedIn, I think it was. Yeah, probably, from the GUY. And they had a discussion about should you use MD5 to hash password, yes or no, pros and cons. And then this bright young fellow just suggested, I have a better scheme, it's much more performant, just do this. So I'll just enlarge this to make it easier for you. So basically the scheme he suggested was take the input, base64 encode it, or as people like to call it, base64 encrypt it, reverse the order of the characters, and now you have an encryption scheme. That was the offer on the table, and he was pretty badly scathed for that unprofessional remark. But my point is that if you frequent Stack Overflow or other places, there are a lot of non-security cryptography advice floating around, and relatively few places where you can get solid, good advice of how to actually perform and implement and use cryptography correctly. And unfortunately, there are a lot of places that you can do this wrong, even if you had the best of intentions. So the tool that I was trying to remember the name earlier was called CryptHook. CryptHook was actually a very nice concept. It said, I want to provide security to pieces of software where I don't have any way to change their code. So what I'll do, I just hook the system calls on the network system calls, and I will encrypt the traffic going from the client to the server, wrapping around the original software which has no security capabilities. So that was the basic concept. It's not that bad. And they were using something called GCM, Galois counter mode, and they used a fixed key to do so. So they used the same key, they did not use sequence numbers, and they really did the bare minimum to actually get the code to work, without giving a lot of thought to what would it mean that you dropped all of those options, that you selected these options instead. And what happened was that you don't have sequence numbers. It means that I can take any kind of packet from the network, send it again, and it would be accepted because there are no sequence numbers. There's no way to tell what kind of order the packet should have arrived in. I could also change the order of the messages. I can create a sequence by my control that will have a completely different meaning. Just a small example here. There's a big difference from your bank account let's assume that your balance is $100 and you have two transactions coming in. The first one is plus $500 and the second one is minus $500. So if the order of the transaction is first add 500 and then subtract 500, you're good, you're in the clear. But if you had $100 and you first had subtract $500, now you're in debt for $400, and now you had $500 coming in, you're back in the green for $100. Except now you will have to pay the bank some fees because you're overdrawn. And by the way, this is a cool little trick done by banks in order to increase their margins. So whenever they have a lot of transactions coming in, they will order this in a way that will usually benefit them. Also, you can always drop specific messages. If you know what the message is supposed to be because of the order the origin message was supposed to be, you have transaction A, transaction B, and verification, drop the verification, see what happens, it might work. And there was no session key, and this is a bit tricky, but what it means is that because the key was fixed for all sessions, it means I can decrypt all of the sessions at any time. The key would not change from session to session, which means that if I recorded all of the traffic and it took me 6 months to analyze what happened, I will understand what happened not only for the original content I was analyzing, but for any content that I recorded since, because it's always using the same kind of key. So no forward secrecy is a big issue. So, to wrap this up, is everything on fire? are we facing the dumpster fire of death for security? So probably not, but we could do better. So in order to do better, I suggest the following. The first rule of engagement, the first thing that you should have everybody tattooed whenever they try it for the first time is never roll your own crypto. Writing cryptography software is very, very difficult. It's prone to mistakes. It's prone to mistakes on a math level. It's prone to mistakes on coding level. But also, it's difficult because using cryptography correctly, even if the code is 100% correct, using it with the right kind of parameters, the right kind of API selection, the right kind of orders to do things is also important, and usually people don't know how to do that. So they resort to copy-paste from Stack Overchange or other places, or Google search for blogs which might have good information or bad information, and incorporate that into their code, which is not a very good practice. So where can you get answers? The first place that I recommend is the subreddit for crypto. They're very serious people, and they do answer questions if you have questions that need answered. Also, you can go to the crypto stack exchange, not for the Node.js stack exchange asking quick crypto questions. Go to the crypto stack exchange and ask crypto questions there. Also, you can hire a cryptography review firm, hire consultants, ask experts. Just don't do this on your own. Ask someone who understands how this works. A couple of other suggestions that I have. You're using libraries that have dependencies. One of those libraries somewhere is going to depend on a crypto library. It's almost guaranteed. Make sure that you understand what your dependencies are, and are they dependent on something strong and reliable. I've listed a selection of libraries on the right hand. I recommend the top 3. I have issues with the bottom 3. Specifically, you should take into account that cryptography libraries, like any other kind of software, has issues, has bugs, have vulnerabilities. You have to track them, you have to understand them, and you have to patch and upgrade them as needed. Don't take into granted that because you're using some NPM package that you'd come with the latest kind of crypto. Don't assume that. Check that. Also, I don't recommend using OpenSSL. Some people really love OpenSSL. I don't know why. Basically, I think that they never experienced like the good life or something like that, and they are masochists at heart. Use any other library. It would probably make your life much better. Boring SSL is by Google, very strong library. I'm very fond of it. The crypto language, the crypto library for Golang is also very, very strong, very good. You can learn a lot from looking at what they've done. NaCl and libsodium are also very strong choices. WolfSSL is a commercial product, but they have an open source kind of thing as well. Look around, you can find other alternatives. What else? If you can, outsource this to people who know better. At least the cryptography part, to make sure that you are vetted correctly. You can also look up at vetting reports that are out there. For example, there are a couple of firms that are releasing, whenever they are auditing open source software, they will release the audit report. Look it up, read it. You will learn a lot of ways that attackers are looking at cryptography in order to think, will this be relevant for my organization? Probably it will be relevant for your organization, so look it up. To conclude, if you have any questions, I'd be happy to answer, at least point you in the right direction, if not give you more than that. And I do recommend very highly that you take cryptography not seriously. Not everybody has to be a math expert, but at least read up about it. Where are the pitfalls? Where are the issues? Because at the end, this is one of the biggest things that can happen to your software if you assume that crypto works and it doesn't. Thank you.